As a first step into the artificial intelligence machine learning world, we decided to focus on a well-defined and on first glance simple interpretation task that is fundamental to seismic interpretation, that being fault definition. We started with a database of hundreds of public domain wells and used the well logs to generate millions of 3D synthetic models that act as representations of real seismic data, with the central sample defining the presence or non-presence of a fault. In other words, we generated a library of synthetic models, then used those models to create and train a network to identify and localize faults. The process is dynamic. As our well database continues to grow, and as we learn about key identification drivers, we continue to add models to the training set and proceed with more epochs of identification. The identification accuracy continues to increase, and the generalization improves. When we apply this to real seismic data, our model-trained networks reveal fault-related subtleties in the seismic data that we had not previously recognized with visual inspection. Let's look at a couple of examples of machine learning fault predictions. Keep in mind that these are all raw ML predictions that can always be further processed or skeletonized as desired. In the first example, machine learning nicely defines many closely spaced faults. It also defines the splitting that occurs within complex fault zones. In the second example, where we previously saw a single fault, as shown here, we now realize that the fault is subtly splitting. The split is quite narrow, and although it is detectable in the original seismic data, it was noticed only after it was detected and revealed by machine learning. Also worth noting the ML anomaly at around time 440 to 480 milliseconds. It is a good reminder of the importance of working in 3D. What initially looks like an area of false fault positives on a single 2D line is actually a concentrated set of disturbances, or edges, associated with a channel that is oriented orthogonal to the fault. This particular 2D line is quasi-parallel to the channel edge. For exploration and seismic interpretation purposes, a key takeaway is that machine learning is not about trying to remove humans from all aspects of the workflows. Some specific tasks will be quite conducive to full automation. For other tasks, human guidance will continue to be required. Rather than some magic piece of automation, the greatest value of ML comes from trying to obtain greater detailed understanding within an interpretation. Machine learning can indicate areas that merit closer human inspection of subtle details. It makes you go back and examine the data with additional perspective and additional insight.